if you say compilation. So that's the key. Everywhere else is aggregation. So it's how you know that you don't know. Shall we get back to code? Let's do some code and look at this example a little bit. Dim the lights just a little bit more. So we've been running this code, playing around with it. I think we've kind of looked at various aspects of the code. Everything's on a log scale. So if you haven't seen the last lecture and you weren't here, you can go back to the last lecture and kind of review that. What I want to do is I want to stress this code a little bit. So this is Metropolis within Gibbs. And so can somebody tell me why I'm doing Metropolis within Gibbs for this example? I've said it about 12 times. Oh, wait. Show you how it works. So it probably isn't a great idea to do a Metropolis step for everything. So what we're doing in this code, so again, our example is xi's come from a normal distribution with 2 parameters. And so we're going to get some number of data, and we can play around with that data as well. And so we're just updating mu. This is going to come from its full conditional distribution. I'm going to have to initialize phi t minus 1, and then I'm going to get a phi update. And it's going to come from its full conditional distribution. I don't need to initialize mu because I'm going to get my first mu there and I'll plug it in. If you're familiar with the Gauss-Seidel algorithm for inverting a matrix, incredibly popular iterative scheme, this smacks of it. It looks just like it. So feels just like it. And that thing converges and there's a fixed point in all of that. And you can prove through the fixed point theorem that this thing converges if you're within a contraction map. The theory governing this is entirely different. So, and we're going to go through that theory afterwards. Keep in mind these are stochastic functions. And so we are not using things like the fixed point theorem that you would see in numerical analysis. So while this looks like it, kind of feels like it, there's some semblance, again, the theoretical background for it is entirely different. So I'll just walk you through this again. What we're doing right here is we're going to do an MH step here. And we're going to do an MH step here. And we've kind of talked about which proposals we might use. I'm using a normal proposal here, and I'm using a truncated normal proposal here. I've also made a slight error in my code. And so the proposal that I'm using here is symmetric. So let's just detail this Metropolis step. This Metropolis step right here looks like this. I'm going to propose a mu from some proposal distribution, and I'm going to center it at where I was last time, in the previous step. So considering this right here, I really do need to initialize everything. So in terms of my proposal. So I'll need initializers for both steps because I'm using this localized form of this proposal right here. This proposal looks like this. 1 over square root of 2 pi. There's going to be some tuning parameter right here. This is going to tell us how far we step away from our previous location. And this is mu star. I'll just say mu. If you'd like me to put the star right here just so you can see the notation, this isn't quite right to do this. This is the random variable. This is the space that it lives in. This is the realization. I can take that thing and plug it straight back into that equation right here. So the mu star is coming from that random variable. I'm taking its density function and I'm plugging it right back in, right there. ut minus 1 squared over psi squared. So this is tunable. And it tells us how far away from our previous location we want to step. So we're centered here. This is a normal distribution. It's centered at your previous location. And I'm willing to propose values based off of this normal distribution. And so if I make psi very big, it's going to propose things potentially very far away from what I've seen last time. And if I make psi very small, it'll propose very closely to what I've seen last time. We're going to do something similar right here, and we're going to use a truncated normal. So I'm going to end up proposing phi star from some normal distribution, and I'm going to center it where I was last time. But we're going to make sure this thing is positive. So I'm going to include this indicator variable that phi is greater than 0. So that's this phi right here. So the phi star will come from that distribution, and it'll have some tunable variance as well, and I'll call that psi for phi. So this psi is specifically for mu. In my code, I've let them be the exact same values, but we could tune those differently if we saw that the convergence rates of those two parameters were different. And in general, they are different. So that's tunable. You'll want to pick those. I'll point out that g mu t minus 1 given mu star is equal to g mu star given mu t minus 1. So I look at where the mu star and the mu t minus 1 show up, and I interchange them. And it's the exact same formula because I'm just changing the negative sign in here, but I'm squaring everything. And so what that means is that given that I'm at mu t minus 1, I'm going to propose a mu star. In the backwards proposal, going in the other direction, is let's say I've accepted mu star and I want to consider how fast it would take me in some sense to go back to mu t minus 1. So all exploratory algorithms should have the ability to come back to where they were. And in fact, the probability, it's not quite probability because this is a density function. So the probability is 0, but it happens. Probability 0 things happen all the time in continuous distributions. So instead of talking about the probability, I'm talking about the density of the transition. If it were a discrete thing, I would talk about the probability. If it was a mixture between those two things, if I had discrete and continuous, I couldn't use either one of those words. And so I would change my word to rate. And that's the convention that we normally use. So the rate of returning. And I could use that word whether or not it was a probability or a continuum or a mixture of both of those things if I were updating two different types of random variables simultaneously. This is called a symmetric proposal when this happens. So when these are equal to each other, the rate at proposing something is same as the rate of going backwards in time. So the forward time step and the backward time step are exactly the same. So the rate of proposing in both directions is the same. So this is called a symmetric proposal when this happens. Of course, this is a little bit silly because I'm proposing using a normal distribution and the full conditional itself is a normal distribution. So on your homework, you will do this correctly and you'll just sample out of the full conditional directly. If you do that, it'll converge very fast. But I can make it converge very slowly by making this value very small. So if I make that small, we're going to see its convergence path. And so that's what I'm focusing on here. So that's why we're doing Metropolis Hastings within Gibbs, so that I can control the rate of convergence and show you different features of its convergence. This is a symmetric proposal. This one is non-symmetric. And that's the slight error that I made in my code that I've updated to you that you can use for your homework. It's not symmetric because the integrating constant is different at every time step. Darren Wilkinson's blog that I posted for you shows you what you plug in there. It's going to be the truncation normalizing constants. It's going to be a ratio of those. And he kind of shows you in that blog post, you can barely tell the correct sampler from the incorrect sampler. It's a common mistake, but it's probably good to get it right. Somebody sees an error in your code, they might think there's lots of errors in your code. Okay, so just to run you through this again, thinning is going to be that thing where I just only store every so many samples. I'm going to store every sample since I have a 1 in there. I could make it a 2 and I would store every other sample. And so what that would do is it would take out the autocorrelation from my chain if the autocorrelation was about significant at 2 time steps. If there was more autocorrelation in the chain, then I might need to thin more. Saying that, you can store everything if you want. And so nowadays we've got so much RAM, you probably could store everything if you wanted to do it. So it's really just kind of an engineering device so that you don't blow up your RAM. If you wanted to pull out autocorrelation and you had a lot of samples, you could just shuffle them as well. Here's my number of iterations. I'll put that back to 1 right there. My number of iterations is big. And I'm going to have some burn-in period. And we looked at this last time. That's going to be the period that I break off of the path as it's trying to converge, all the stuff I want to throw away. Keep in mind, we're not converging to a single answer. We're converging to a distribution of answers. So convergence is in some sort of probabilistic sense. I will mention this converges almost surely. So what that means is as I start getting closer and closer to the target density, it doesn't jump away from that. So once it gets close, it stays close. So convergence and probability might say there's instances where I'm able to jump away, but the probability of those instances decreases. That's forbidden in this. So if you notice that in your code, you have an error. So we won't prove that, but you'd have an error. So it doesn't just converge in the probabilistic sense, it converges almost surely, which I kind of like because it helps us to debug all of this. So there is some utility to knowing how it converges. Once it gets close, it's not supposed to jump away. So I have starting points. I'll keep the same starting points that we had last time. I pad my space with zeros for speed and efficiency. I initialize my starting point in the vector with my initialization. We can change that, and we will change it in a couple minutes. I plot everything, and then I just have these 2 updating steps. So I've got my proposal, and I've got my where I'm currently at, so I can form the target ratio. Everything is on a logarithmic scale. I went through this last time. So instead of taking a ratio on a log scale, I take a difference. So that's going to numerically stabilize everything. We can look at it, and I can uncomment all this, and we can trash the code real quickly. Mathematically, it's the same thing, but it won't work. So, and it's because of the rounding error that a computer makes. So I end up, I'll just tell you this acceptance step right here. This might be clear to you already. But let's say I were following the algorithm. So in a Metropolis Step MH, so steps 1 I propose, and then 2 I accept with some probability. So my acceptance probability is going to look like this. My posterior target, I'll say mu star in this example, given vt minus 1 and x, pi mu t minus 1, given vt minus 1 and x. And then I can put in my proposals if you would like. Mu star given mu t minus 1. And basically, you just are reversing the proposal upstairs right here. It's the backwards step. So mu t minus 1, but I have to consider how I would have proposed that. And under my proposal scheme, it's going in the other direction. So I'm flipping around these conditionals. I've already said that these are the same if I use that symmetric proposal. And so that's that. So I'll make a note. Note, when the proposal is symmetric, this is called the Metropolis algorithm. So this is the algo that Nick Metropolis proposed to us in the late 40s. So he said, assuming a symmetric proposal, he's working on a problem that is on a lattice called Nicing model, if you're familiar with them. And he proposed in a very symmetric way, and he detailed that algorithm. When this proposal is not symmetric, they call it the Metropolis-Hastings variant. Now, I call them all Metropolis-Hastings or Metropolis, depending on whatever my mouth just said. So I have no rhyme or reason to say one is one thing other the other. I say metropolize something. And if somebody came in and said, do you mean Metropolis Hastingize it? And I'd say, yeah, do that thing. I pick a good proposal, pick one that works. So, but that is the name of the game. So Hastings came in and showed that you need this proposal ratio in here if you're using a non-symmetric proposal. Where's a good case where you might use a non-symmetric proposal? This is one of them, right here. So I'll just say I get this probability, and if I want to do this final step here, get rid of that. So what we do at the end of the day is I take my mu t, and it's either going to be mu star or mu t minus 1. This happens with probability alpha. And this happens with probability 1 minus alpha. So it's a Bernoulli coin flip. I take that coin, I flip it. Now, I don't actually do this. This is called the Inverse Cdf Algorithm. You can do this in one dimension. If you take the CDF function for a distribution, you invert it and you plug in a uniform into that inverse CDF, you'll get a sample from the original distribution. If you want to see why that's true and you're not familiar with that, review session would be a good time for that. Or you could protest and say, really want a 10-minute lecture in class on that. And I'd be happy to go through it. But you probably have learned this in inference class once upon a time. So it's a common problem. The proof for why it works is exactly the same reason why, when you reject with a p-value that's less than alpha, that the type 1 error rate is alpha. So it's exactly that same thing. The proof is identical. I don't actually build a Bernoulli right here. What I've done is I just checked to see, keep in mind this is on a log scale. I've taken the logarithm of both sides, but typically what I would do, if it wasn't on a log scale, is I would write if alpha is, alpha, let me do this again, a uniform random number, so this is random right here, is less than or equal to alpha, then I accept. Else, I would normally say reject, but I would store the old point. So I'm going to get rid of that language, and I would say mu star right here, or mu t, is mu star. Else, mu t is equal to mu t minus 1. Make sure we understand this. So let's say I've got a probability of 0.7. I want to flip a coin and accept with that probability. So what's the probability of a uniform being less than 0.7? Let's just make up a number. A uniform 0, 1. 0.7. What's the probability of a uniform 0, 1 being less than 0.3? 0.3. So it's that number. So what's the probability of a uniform being less than alpha? It's alpha, so this happens with probability alpha, which is the way I originally wrote everything down. So if you're wondering what that sampler is and if you can generalize it, it really is inverse CDF. So that's what I've done here. And so, but I've done it all on a log scale. So instead of checking if a random uniform, that's what the rand function invokes, is the uniform random number generator. If the log ratio is less than whatever this log ratio is, that's the exact same rule because logs are monotonic functions. So we're doing all of that just to numerically stabilize everything. And I do something similar down here, except I make a point that this is not a symmetric proposal. So for phi, I'm using an actual accept-reject algorithm. And what I do is just, I end up resampling from its normal distribution, the proposal, until it's positive. And that's what this does. And so if it's truncated very far to the left, it'll take a long time to run that. If it's truncated to the right, if the mass is very far to the right of 0, it will give me a value very quickly. I will point out that in high-dimensional spaces, sampling from truncated normals is always a burden. So if you're familiar with probit sampling or something like that, you have to incur that, and there are fast ways to do it, but in general, it's not the fastest thing in the block. In our case, since everything's one-dimensional, it's really quick. And then I do everything on the logarithmic scale as well. So this ratio right here, it does need to include the proposal ratio, and it's the truncation normalizing constants that you're actually plugging in right here. Again, Darren Wilkinson's paper is plotting. And everything else is just plotting. So the only place I use the truth in any of this is just to plot. So I do feed in the truth into this function just so I can see our answer converging, and hopefully it's close to the truth. Today we'll generate a little bit more data. We can change these numbers. So I need a true mu. I think last time I picked 7. I'll pick a true. Let's see. What does this take in? Does it take in sigma or does it take in phi? It takes in sigma. So I do the 1 over thing in the code. So true sigma, I think last time we picked 2. So sigma squared is 4, phi is 1 over sigma squared, so phi is 1 over 4, it's 0.25. Now I generate some data. I want to make sure that this is enough data, so I'm going to make this 31 or something like that. That's what we've done before. Let's actually just make it like 10. So just for reference, to see a little bit more of this contour shape and change the example a little bit. So there's my x's. And I'm going to use those x's to try to infer mu and phi. Here's my Gibbs sampler. It invokes that code. This is my starting point right in the middle of everything, just so you can see it. And there's my code running. So this is obviously all the burn-in trajectory, and so that I'm plotting to you. So we probably want to rip that stuff off. So we probably have to look at how long it's taken for this thing to burn in the first place. So I plotted some other plots for you. I've got these 2 plots. These are including the burn-in and everything. So the burn-in's here for both of these plots. This plot is specific to phi. All I've taken is I'm getting at the end of every iteration, I'm getting a mu phi pair. So I'm just plotting the phis right here. And that's all the burn-in period. So it's taken me some amount of time to burn in, not quite 1,000 iterations, but several hundred iterations. And if I look over at mu, it's burned in much faster. And so you never really know, as you're running these things, which one is going to burn in faster, because you would have to have a pretty keen imagination to understand the contours of everything. And so how it's going to start walking up the contours and try to find areas of higher mass. That's what it's doing. So what we want to do is we want to rip off this period. So we don't want to look at the shortest burning in chain. We want to look at the longest burning in chain. So nothing has converged until all of the parameters have converged. So if a parameter is associated with all the other parameters, you need to make sure its joint relationship is converged. So we'll get rid of those because they're kind of worthless to us right now because our burn-in period wasn't sufficient. So let's crank up our burn-in period. I'm going to make this 1,000. That looked pretty good. Maybe I'll make it 10,000. Everybody likes to make these big numbers. I've got 100,000 iterations. So this is 2022. Who cares? So back in the day, people really cared about this sort of stuff because they couldn't store very much. Same starting point. It's converged to something. Here's my contours. So that triangular shape got way more pronounced in this example. And it got way more pronounced because n was small. So we'll see the behavior of all of this as n gets bigger and bigger. So, but we see this contour shape. It makes sense to me. So what I've done is I've ripped off the burn-in period of all of this. So in my plots, these plots right here, so what I've done is I've ripped off that whole tail. Now I did plot the burn-in period on here. So I think that's okay. But I've ripped it out of my histograms. So the histogram part doesn't have that. It actually is just these samples. And we can zoom in and look at those samples in a couple minutes. So I do have a couple questions. So these are trace plots just for the margins, for mu and for phi. Now, it's kind of hard to tell what's going on right there just because my scale is kind of warped because of the burn-in period. So I might want to zoom in. So I could zoom in, have a look at that chain, see what it looks like. Keep in mind the scale's pretty tiny. Right here. So, question is how did this thing do? Did it find the truth? Here's my true answer. So it's right here, but for mu it's right there. Somebody tell me, why did this happen? So my posterior distribution, at least the marginal distribution, and I'll point out, if I have the joint samples and I just throw away one margin, I've got the margin of the other one. That's like integration. So I've got joint samples, and when I get rid of one of the columns, I get the margins. That's pretty cool. So if I wanted a conditional distribution for phi, like phi is equal to maybe 0.2 or something like that, I'd look at all the samples that were 0.2 for phi, and I'd take those mu's. It'd probably never happen though. So just because of the continuous nature. So what you would probably do is plug in phi and never update it, and just update mu. So these are actually the marginal distributions. These are the integrals. So this is the integral when I integrate out phi, and this is the integral when I integrate out mu. Somebody tell me real quickly, as I integrate out mu, what distribution is this? It's a gamma. Do you guys remember which one it is?
Phi over 2 1/2.
Say it again?
Phi over 2 1/2.
Phi?
Phi over 2 and then 1.
Oh, you're telling me what the likelihood, the posterior kernel looks like.
Oh.
It's got arguments in there. They're what we call alpha and beta usually. It can't have a phi.
Oh, right.
It's n minus 1 by 2 and so on.
Does anybody remember? So I think it's gamma n minus 1 over 2. sum of the xi's minus x bar
Yeah, right.
squared
Right.
divided by 2.
Yeah, I don't remember.
You could write this like this, n minus 1 times s squared. So that's where that n kind of appears right there. So what's the expectation of this thing? Oh, and it's divided by 2. So what's the expectation? It's that over that, so the n minus 1s and the 2's cancel. So the expected value of phi given x is equal to 1 over s squared. Kind of makes sense. So that was your last homework assignment. You worked that out. That was the first problem. What's this distribution supposed to be? I've got a normal. It's a t. So this is the integrated one where we've integrated out phi. So this is actually a t distribution. And if I didn't know that, there's nowhere that that's encoded, these samples are actually coming from the right t distribution. And we've worked that out as well. So that t is centered at where? X bar. And its scale has something to do with s squared as well. So how many degrees of freedom is it? N minus 1 degrees of freedom. So it's the same t distribution that a classicist might base their inferences on. So I don't know if they would use this, but we all agree on that one. It's kind of weird. So anyway, you're also getting joint samples. I think this thing has converged. If I'm looking at this, it looks kind of okay. It's not bad. It's all right. I could tune the proposal step. You'll kind of notice that this one right here kind of zigs and zags a little bit more, and this one gets stuck sometimes. So this one has these flat plateaus. You can zoom in a little bit more. You can see those flat plateaus. And it's because I've used the exact same tuning parameter. So what that might mean is that I need to reduce the tuning parameter for this distribution, and maybe I want to increase this one so that I don't have all these super autocorrelated things. But let's just keep it the same for right now, and you can play around with it a little bit on your homework. Again, back to the original question. The true value is here. Let's do it again. Let's just rerun it, new data. See what happens. X, 10 data points, rerun. Keep in mind, these are a different 10 data points. Same sort of joint shape, kind of. You kind of see like it's a little bit blobous over here. I need to run it longer to smooth that out. So once it got into this little tail region, it had a hard time kind of moving around in here. So I probably need to run it longer. Here are my two marginal distributions, and now the red thing's in the middle, kind of in the middle, not exactly in the middle. Does anybody know what's going on? Why the red thing the red thing was the same point, but our distributions moved. It's a random sample. In a sample of 10, you would expect that sometimes you might not nail your truth. So if I was generating the data with random parameters that were generated from my prior distributions, you couldn't quite do that because these are improper. But my intervals would cover at a frequentist rate. And so your 95% intervals only cover 95% of the time, and 5% of the time, you would expect things don't cover. So sometimes it shouldn't cover, especially with just a small data set. There's no asymptotics in any of this, so it's not that thing. But it shouldn't cover every once in a while. So if somebody ever tells you like their predictive rates are like 99%, don't believe them. So, or their problem's just so simple that for any sophisticated problem, there should be error rate. Let's run it again with different starting points. See how this thing looks. Make sure this thing is kind of running. So let's start maybe farther away. And I'll keep that maybe closer, something like that. Let's come from the other direction, in fact. Bang. There's my samples. What do you think's happened? Is that converged? No. So there's no semblance of it bouncing around a distribution. That distribution is diverging. So it's changing and it hasn't converged to anything yet. So what do I need to do? What's that?
Increase the number of iterations.
Increase the number of iterations, yeah. So let's do it. So can't look at that stuff because it's just junk. I haven't run it long enough. Or I have really bad starting points. Both are true. So let's just increase the number of iterations, and I'll increase the burn-in period too. So pretty inefficient thing to do. A sane person would probably start it where it left off, you know? But we're trying to stress this code, see how far we can push it. Seems like it's kind of converging. Boom, it's stacking up right there. That feels pretty good. It's a lot of iterations. If I didn't pad everything with zeros, those numbers flying across the screen would start slowing down and bogging down. And if I looked at my RAM, it would start increasing and increasing and increasing, and it would have some trouble. Actually, it looks pretty good, doesn't it? So we get kind of this triangular shape. Maybe we've missed a little bit in here. That bending seems a little funny to me. So I probably need to run it longer than that. So here's the burn-in period. We've ripped that off. We've ripped off quite a bit of this stuff. I think we ripped it off up until there, right there. That's some t distribution, and that's some gamma distribution, and everything seems to have worked pretty good. That's 10 samples. Let's see what happens if I got rid of the log stuff in all of this. And you can already see it's going to fail. So get rid of that. And I need to be a little bit careful right here. That's actually a ratio. Now, it's not on the log scale. And I need to get rid of my logarithm right there. Probably could add an if toggle. So now everything, this is the same rule mathematically on the chalkboard, everything's the same. And if you compare these two functions to each other, one is the log of the other. I've even been, oh, you know what? I don't even need to do that. I could get rid of this logarithm right here. So I put everything on this log scale just to be really silly about it. But now everything's not on the log scale. So I've gotten rid of those logs right there. Run this thing. It's kind of done something. Actually kind of surprising. Well, I was hoping it would break. Do you know what happened? Why it worked? I do know. So why it normally breaks? Let's do it again. Let's check that. It actually probably will work for a while. So we end up running it. Let's make it farther away and see if we can get that thing to break. Mu's pretty far. Let's put that back to like 50. Messing up the variance really messes things up. So more so than the mean, just because everything is calibrated to variance in these functions right here. So I'm dividing by, or I have this phi multiplied in here. So let's rerun that. It looks pretty broken. So we'll see. I can kind of see it moving a little bit down here, but it doesn't know what to do. It's inching. But as soon as you have a numerical problem in your code, it's almost impossible to recover from it. So the first time the computer throws an int for a nan or something like that, you can't really recover from it. And if you did, it's just because you're lucky. So, okay, so that doesn't work. So going back to the log scale is probably a good idea. But we did see something kind of funny. That when I made this 20, that thing worked. Let's run it again and see that path that it takes. It didn't work this time. Keep in mind everything is random. It's a junk. I wouldn't put too much thought into that if you get it. That's a weird posterior. No. So this would be a clear indication that the thing hasn't converged. So what most people do is they base their diagnostics off of the trace plots. And what I'm going to teach you to do is visually inspect these trace plots. You look at them and say, that doesn't converge. We'll look at a few more examples so we can see different forms of probably need to tune it a little bit more. But that clearly hasn't converged. So I would not report that as an answer. Let's run this thing again. Maybe 200, something like that. See if we can get this thing to converge. It's going. I don't know if you can see it, but boom, it's collecting mass. Bang. That burn-in period is still present right here. So we haven't burned it in long enough. So we can rip off the burn-in. Let's try it again. This is what MCMC looks like. So if you ever know anybody that runs MCMC, they're doing this for like hours. Playing around with things, run it again, I want to see what happened. So this is my life as an MCMCer. So I kind of enjoy it. It's very patient work. So let's just try it again with the higher burn-in period. Boom, 200,000. We got a lot of samples. I think this makes me so, I don't think it's going to go. So numerical difficulties just because of the stochastic nature of things. Oh wait, there it goes. Hey. They made it. Still, it took a long time. So let's crank up the burn-in period. Might feel pretty good about this. I'm going to take half the samples. So you will see people say I thinned a lot and my burn-in was huge. They're trying to give you confidence that they made the algorithm converge. It used to be the norm that you would show your trace plots to everybody. And so in the early 2000s, all the Bayesian papers, everybody was displaying their trace plots. Nowadays, reviewers will tell you to get rid of them. If you're in a field that's not statistics, you could probably plot your trace plots for them. They probably want to see them. So just do things that people did 20 years ago in a new field, and that's what's called new, and you'll get celebrated. So still too much burn-in period, or not enough burn-in period, so we can kind of look at this. Looks like it didn't burn in until the very end there. So I need to get rid of everything. If I were smart, I probably wouldn't keep rerunning it, but I want you to see what this really looks like. So let's make that 90,000. Maybe that seems pretty good. I'm still getting 100,000 samples to look at, right? What's that? After I burn it in. So I get rid of those other 900,000 samples. That was my burn-in period. Hey, feel pretty good. You know, this thing works. I feel awesome about this code. I'm about to, let's run this on some real data. So now I go and I get my real data set and I run this. So it seems to be working. So I've debugged this in a simulation sense. It's ready to run. And what I would do is before I did this on a real problem, I would run it on simulated data out of that problem. So for whatever my MCMC thing is, if I can write down the likelihood, I can write down the sampling distribution, and I should be able to sample data out of that sampling distribution. And then I can check to see, am I landing in the right places before I plug in real data. So I feel pretty good about this. I'm going to go get my real data set. My real data set is a little bit more realistic. It has more data in there. So I plug that thing in, 100 data points, I rerun this. Seems to have converged pretty quickly there. Almost done. Actually worked. That's amazing. So we're a little bit lucky. Let's change our answer a little bit. Actually, let's keep that thing the same. Let's go get more data. So I end up running that again. More data's in there. And I run this thing again. And we're starting to feel pretty good. It seemed to have worked twice. Be done in a minute. I run it again. Taking a long time. It takes longer to run these iterations. You notice that? Do you know why? Yeah, it's a function of n, the way that I've written out the target function. So I didn't really handle it very well. And here it is, it's total trash. It did not work. And the reason why is I cranked up n in that. I thought it would fail for 100. But if I go back and I look at my code right here, the way I have this step written down right here is I have a product in here to formulate my likelihood function. If I'm producting this thing together that's numerically unstable in the first place 1,000 times, I'm adding more numerical instability to the problem. And so that's not helping us at all right there. So it didn't work at all right there. If I took a logarithm around this, I would do this, but I think you know this won't solve the problem. So I could do that, rerun it, it's still gonna fail. So taking a logarithm of trash is still trash. So what we really want to do when we take the logarithm is algebraically retake the logarithm and simplify our function. This doesn't have any producting, it has sums in there. And sums tend to be numerically stable. So think about small numbers in products. As I start producting small numbers, they get smaller and smaller and smaller quickly. Same thing with big numbers, they get bigger fast. And computers don't like big numbers or tiny numbers. But sums don't get big too quick. They don't get small too quick. So now I've got to change this back to my logarithmic form. And I take the logarithm. This will probably work, fingers crossed. Same data, run that thing, it converged quick. Bang, I can kind of see it is hit there. We'll look at our answer. Voila. And the triangular shape is going away. So as n gets bigger, these things are feeling more and more unrelated to each other. They don't exactly factorize, but as you get bigger and bigger, things look like they're less associated with each other. So this circular thing looks like they're close to independence. They're weakly dependent on each other. What I want to do next time when we come back is I want to play around with the step size. So I want to just show you one more thing before we go. And we'll pick up with this next time. So let me make the problem a little bit easier. I'll put this at least in the ballpark, 10, 20. Then I don't need to run it as many times. Something like that. And I want to change the step size. If I make this step size really big, something will happen. So I'm going to make this step size really big. So that's my proposal variance for both models. I run this thing, it's converged quickly, but it still doesn't look very good. So if I zoomed in on these trace plots right here, so I look at that trace plot, it actually has hit the stationary region, the target region, but it's plateauing a lot. It's getting flat. And the reason why is my proposal variance is huge. So I'm always throwing it outside of the answer. And since I had a lot of data in there, my variance was actually small. So, so it's shrinking the variance to everything and bringing down that region. So this is plateauing. So this is a clear sign that things don't work. You might think to yourself, make it really, really tiny, but you're going to come up with another phenomena that's not good. So we're going to discuss this Goldilocks principle of hitting the sweet spot in your tuning of everything. And after we spend about 5 minutes looking at that, on Monday, I'm going to walk you through the theory on why all of this algorithm works. Or at least I'll give you the main chunk of the theory. So one little part I'm not going to tell you about. Well, I'll tell you about it, but we won't spend too much time on it. Okay, so next time we'll get the theory. You'll code this stuff up. Then I'm going to tell you about Wishart distributions, and then we'll jump to Jeffrey's project. Also, review session next Tuesday. We'll do another review session on the Tuesday after, because the next morning you'll have a midterm. What's your calendar? Thanks, you guys.